If you analyze a pendulum, you will find that the four factors that appear as though they may affect the motion of the pendulum would be the length of the pendulum, L, the gravitational field strength, little g, the mass at the end of that pendulum, and then the angle at which you drop that, or what we call the amplitude. If you test that out, you will find that in fact, the length and the gravitational field strength are the only two variables that really seem to have any effect. Mass has none whatsoever. And for the angle, you will generally find some people that say there's no effect, some people say that there is effect. The effect is kind of minimal to some degree. So the reason for that is that if you go beyond 15 degrees, so if you pull that beyond 15 degrees from its resting location, there will be an effect. Anything less than 15 degrees is considered what we call an ideal pendulum. The good news is that is all we are going to look at in this course. We're not going to be too concerned with going outside of that 15 degrees where the math becomes a little bit trickier. Things are not quite as straightforward. So we're going to limit everything to what we call ideal pendulums. So for our purposes, the drop angle or the amplitude has no effect on the motion of a pendulum. We go beyond 15, it is, but again, know that, but we're not actually going to be looking at that case. So if we understand these relationships, or we take measurements and we determine these, we generally will see that the length has a direct relationship. The longer the length of the pendulum, the longer it will take to complete one cycle. So these are all in terms of the period of the pendulum. The gravitational field strength, we should find that it is an inverse relationship. So the stronger the gravitational field is, the shorter the period of that pendulum is. It actually tends to swing back and forth a little bit quicker. Mass has no effect, as we stated, and the angle only has an effect outside of the ideal pendulum conditions. So because we know that the length has a direct and the gravitational acceleration has an indirect, that tells us that within the equation, the length must be in the numerator and the gravitational acceleration must be in the denominator. That's the only way you get a direct and inverse relationship accordingly. So the entire equation, once we kind of understand that, is 2 pi square root of L over G. 2 pi r is the circumference of a circle, and if you have a pendulum that's kind of completing a portion of a circle as it goes back and forth, well, you can't use the full 2 pi r, that would be the full circumference. So this piece here kind of represents like that fraction of a circumference. That's about the extent that I'm going to go into in terms of explaining why it looks so crazy. But 2 pi square root of L over G, if you multiply all that, that will give you the period of that pendulum. So, in a more kind of official capacity, T is the period of the pendulum's motion measured in seconds. L is the length measured always in meters, and G is the gravitational field strength measured in meters per second squared. It's fairly straightforward. So the only thing that affects the period or the motion of this pendulum is the length and the gravitational acceleration, and I can use that equation right there if I want to look at it quantitatively. So let's do that right now. Let's say we have someone on a swing. We don't know what the length of that rope is though, but we observe them completing 8 back and forth cycles over the course of 32 seconds. That's actually enough information without directly measuring the length of the rope to determine how long it must be. So in this case, we'll start with calculating the period. So we know period is the time taken to complete a certain number of cycles divided by the number of cycles. So in this case, it takes 32 seconds to complete 8 cycles. So that means the period of this person's motion is 4 seconds. Every 4 seconds, they complete one cycle. Now that I know the period, now I can use my pendulum equation. The period is 4 seconds, 2 pi is a constant, L is unknown, and this is Earth, we'll assume, so 9.81 is our acceleration due to gravity. So if I divide both sides by 2 pi, that should be equal to the square root of L over 9.81. I then take the square of both sides to get rid of the square root and then multiply by 9.81. So I'm kind of doing everything in one step, but I square both sides. That gets rid of the square root. So I get 4 over 2 pi squared equals L over 9.81. Then I multiply both sides by 9.81 to solve for L. If you do all of that correctly, you should find that the length needs to be just about 4 meters long, a little bit under. The one thing I would recommend you be extremely careful with is this section right here. If you do not ensure that the 2 pi is in parentheses or in the denominator in your calculator, it will give you the wrong answer. So even though you might have written everything correctly and thought about it correctly, be very careful. Your calculator needs to know that the 2 pi both belong in the denominator. All right, so what if it wasn't a quantitative? What if it was kind of a qualitative, maybe ranking type question? So in this case, you're given 3 pendulums with lengths 3L, L, and 2L respectively. So B is the shortest, C is twice as long, A is 3 times as long, and you're given 3 different masses, 15, 6, and 9 kilograms, and you're asked to rank the period of those pendulums as well as the frequency of those pendulums. We don't have to go too crazy here. If we just think about this equation, the period of a pendulum is 2 pi square root of L over G. So right off the bat, I can ignore every one of those masses. Mass in no way has an effect on either of those two. So I can ignore those altogether. Realistically, the only thing that's really left would be the lengths, because the gravitational acceleration I can essentially ignore because I would assume they're all on the same planet. We can assume that these were all dropped from angles less than 15, so that doesn't have an effect either. So in this case, there's really only one thing that affects the period of these pendulums, and that's going to be the length. So if I just rank the length, A is greater than C is greater than B, well, in this problem, length is the only thing that actually determines how long the period of this pendulum is going to be, and it's a direct relationship. The longer the length, the longer the period. And if I want to rank the frequency, hopefully we just remember quite simply that frequency and period are inverses. So if the period ranking is ACB, the frequency ranking is going to have to be the inverse, BCA, quite simply because it'll be the inverse ranking of the period.